Hello, this is Dr. James Camp from Lee College in Baytown, Texas. I teach programming and computer science courses, and this is an introduction to computers and programming for those who are interested in getting into the science of computer programming. We're going to be talking a little bit about just what makes a computer, and then a lot more about what makes a programming language and what you're going to be learning in taking on the study of a programming language. We're going to learn to write program code for a binary, digital, programmable, electronic computer. Now, let's take those descriptive terms one at a time, because each of them means something for what we're going to be doing as we learn computer programming. First off, electronic. You may have seen pictures in history books of early computing machines. Sometimes they were called mechanical calculators, or one was called an arithmometer. But these were mechanical devices. They had gears and wheels and knobs that you turned, and as you did so, they took certain numbers, added them, multiplied them, whatever, came up with other calculated values. But because they were mechanical, they were slow, they were finicky, difficult to build. The invention of transistors enabled electronic computers, which are tremendously faster than mechanical computers, tremendously more reliable than mechanical computers. And today, in the age of semiconductor manufacturing, much more easy to build than mechanical computers. At first, you can see the picture of the ENIAC here, which was a collection of circuit boards and vacuum tubes and wires and switches and buttons that took up an entire room. That was not what we would call easy to build, but it was the first really Turing complete. That means it had all the features of a modern programming language. You can do ifs and whiles, and you can have conditional statements that jump to different places, and but its programming language was basically plugging patch cables from one unit to another and flipping switches. It took very dedicated people to write a single program for the ENIAC, which would then, run at 5,000 instructions per second. So it might be done fairly quickly, but it might take a whole day to program it. Digital. The early mechanical devices were what we would call analog. If you've ever driven in a car, that most cars up until very, very recently had analog speedometers. The device, the needle moves in analogy to how fast you're driving. The faster you go, the further the needle moves. But that's possible to do without any kind of computer knowing how fast you're going. It's simply, there's a counter on the wheel that measures how fast you're going, and in proportion to that, the needle on the speedometer moves. And early mechanical calculators were a lot like that. Devices that store and display information, like modern-day computers, really require working in digital units, where we can store the information as discrete digits and display them. So the right-hand side of this slide shows a modern speedometer that shows you your speed in digital miles per hour, has a digital odometer, and In this case, even has a digital air temperature indicator. Okay. Going with digital is the idea of moving to binary. Early computing devices represented their numbers in base 10. So this is very simple for humans to process because most of us think in base 10. So 04 plus 07, we naturally think, well, 4 and 7 come together as 11. 4 plus 7 is greater than 10, so we carry one digit over, and we get 04 plus 07 is 11. But this is mechanically complicated. You have to have 10 place settings for each digit, and then you increment that place setting until it hits 9, and then when it rolls back over to 0, it has to bump the next digit up one. So mechanical, decimal base 10 mechanical computers were much more complicated than electronic devices. Electronic devices, however, don't have little wheels and gears that can hold 9 different places. An electronic bit is either on or off. So any position in computer memory either has a high voltage or it has a low voltage. It's either on or it's off. Okay. And so these devices naturally think in base 2, what we call binary. This is conceptually a little bit harder because when you see the string 0100 plus 0111, you don't naturally think, oh, that's 4 and 7. Okay, it's exactly the same problem I showed on the left. It's just that it's displayed in binary. But the math is actually surprisingly easy. When you add those two, when you add a 0 and a 1, you get a 1. When you add 2 1s, you get a 0, but you bump the next digit over up 1. So 0100 plus 0111 is 1011. And this turns out to be surprisingly easy to implement in what we call logic circuits, the kind of circuits that computers are ultimately built out of. Okay, so we've talked about an electronic digital binary computer. What about the word computer? Where does that come from? At heart, a computer is an arithmetic and logic unit. That is, it does certain kinds of computations. It makes binary calculations, that's the arithmetic part, and it makes binary decisions about what to do next, that's the logic part. So you can see at the bottom of this diagram on the right, the arithmetic and logic unit is sort of the core lowest unit there of the CPU, central processing unit. There's a control unit that's a level up from the ALU that interprets and controls the flow of information between all the other units. So the arithmetic and logic unit can only deal with the bytes that have been pushed into its local memory, what we call register memory. There's another bigger memory unit, what you would think of as the RAM, or random access memory, in your computer. And the control unit makes sure that bits are pushed from input to memory, memory to ALU, ALU to output, wherever they need to go. The memory unit stores the information in between individual cycles of the ALU. Okay, the ALU may be busy doing some other computation right now, so the memory the data we're interested in gets put back in memory and stored there until later. Random access memory is volatile. It's also expensive, but it is very fast. It works almost at the speed of the control unit and the ALU. But sometimes we want to store things in non-volatile memory. We want stuff to not go away when we turn off the computer. Volatile means that a RAM chip only stores information as long as it's got power. As soon as somebody cuts power to that machine, the RAM loses its information. Non-volatile memory used to be a hard drive, HDD, hard disk drive, was the most common kind of non-volatile memory. These days, a solid-state drive, or SSD, is starting to take over, especially in laptops because they're lower power use, but really everywhere else. My desktop at home has an SSD because they're just faster. They're much, much faster than hard disk drives. They're almost as fast as random access memory, which makes them a tremendous improvement in computer non-volatile storage. You may have used a thumb drive to carry files from one computer to another, though increasingly we use cloud drives for that instead, which really is actually slower than a thumb drive. It's a hard disk drive on somebody else's computer that stores your files through a network. But because the syncing to that cloud drive kind of happens in the background, we don't think about it as much. There used to be a technology called CDRW, compact disk rewritable. There has been forever and still is a technology called tape, where you put a length of magnetic tape into a tape drive, and very slowly but very reliably your data is stored on this piece of tape. Very useful for backing up large amounts of data. Also very useful for projects like certain scientific experiments where you may have millions of data points and you don't need to access them all at once. You just need to have them all stored somewhere so that you can get to them. Okay. And I remember a time before thumb drives when we all carried around boxes of floppy disks that we would move files from one computer to another with, and those were the definition of slow and unreliable. You could accidentally bend your floppy disk just a little bit too, you could flop it a little too much, and lose all your data. The computer ate my homework was a legitimate excuse back in those days. Okay. Finally, for a computer to be useful, there has to be some form of input and some form of output. How many forms of input and output can you think of? I'll give you a moment to brainstorm your own list. Things that come to my mind are the keyboard, the mouse, the microphone that I'm speaking into right now is a form of input that my computer is turning into a digital video. There's a webcam on my computer that's a form of input. Sometimes I want to scan documents into my computer. That's another form of input. Outputs include the nice, beautiful HD screen that I'm looking at as I do this recording, but also I have a hard copy printer in the next room. That's a form of output. This video is going to be put on the World Wide Web so that it can be used by you, my student. That's also a form of output. In this class, we'll be using the keyboard for input and a console screen for output. That's all we're going to touch with basic programming. That's all most people touch with basic programming. But as you learn more, many more options open up. You may learn how to use windowed display screens that let you click on buttons with a mouse and type things into dialog boxes and things like that. You may learn how to display graphics on the screen. There are many more things you can do with computers than just send text to a console, but we all have to start somewhere. Okay, finally, The last word that we attached to our computer, we had binary, digital, electronic, programmable computer. Okay, the first mechanical computers that I showed you in several slides ago were uh, not programmable. You dialed in the numbers that you wanted them to calculate with, and they did just that one calculation for you. Kind of like a very simple pocket calculator today, where you can type in 1, 2, 3 plus 4, 5, 6, and you can get a result, but it's not a program. You're telling it exactly what to do every time you want it to do something. Programmable devices that you could run a series of commands through repeatedly and get the same result over and over again were envisioned since the 1800s. Jacquard invented a punch card loom so that you would have fabric that looked the exact same way every time it was run through the loom. Charles Babbage invented a card programmable mechanical computer. The device that's shown here was built from his drawings. He never actually built one. And kind of famously, there was this countess, I believe, named Ada Lovelace, who apparently had some spare time on her hands, and so she got hold of Babbage's designs and wrote several computer programs that would run on his hypothetical computer. So she goes down in computer history as the first computer programmer back in the 1830s. In the 1940s, computers became completely programmable, but it was left then to a series of pioneers of computer programming to come up with a way to program them. For the ENIAC, that computer that was programmed by plugging cables and flipping switches, there was a team of 6 women who invented the modern discipline of computer programming. They invented subroutines and loops and nesting and all the things that you will learn in this class. Grace Hopper, one of IBM's first programmers, was the first to come up with the idea that maybe instead of just plugging switches and flipping, plugging cables and flipping switches, we should be able to have a machine-independent language through which that you could write code for the computer. And I point this out partly to just dispel the idea that has taken hold in modern society that women aren't good at programming and men naturally have some sort of talent for computer programming. I've known several good women programmers in my programming classes, but more to the point, it was women who kind of invented the discipline of computer programming in the first place. In 1949, an interpreted language was finally written called shortcode. In the 1950s, autocode was developed as the first compiled language. A word on that, when you write a computer program, it can either be interpreted, meaning the computer reads through the code one line at a time and tries to execute just that line at that time, okay? And that's kind of slow. Or the program can be compiled, which means the computer reads through all of your lines of source code and translates them into machine language. And then the machine language is fed to the processor and runs at processor speed, which is much, much faster than interpreter speed. Recently, there have been some attempts to kind of have both at the same time. Interpreted languages are machine independent, so a Python program written on a Windows machine will run just as well on a Mac or a Linux box, whereas compiled programs get compiled for one processor operating system combination. So if I compile a program on my Windows machine, I can't take that executable and run it on Linux or Mac OS, even if it was written in the same C++ language that would work on any of those computers. It has to be compiled specially for that computer. There's been an attempt to make something that kind of has the best of both worlds in the Java programming language, which compiles to something called bytecode, which is a machine-independent machine code. It runs on what's called a Java virtual machine. You have to have a JVM for your specific processor and operating system combination, but once you have that, you can run any Java program written on any, compiled on any machine. Okay, so what are some basic parts of a computer program? We need to gather input from the user. We need to do some processing. There will be some steps where we just add things together, sort our information, and find data. We need to be able to make decisions. Okay, do we want to go back and loop through our processing step again? Do we want to go back and gather more input? Do we want to just go forward? Maybe there are two different ways to go forward, and we need to be able to branch in our code. We need to call a subroutine. Sometimes there's a need to not reinvent the wheel, and we have code that's already been worked out for us, so we just want to call that pre-written code instead of writing it all over again for our own program. We need to display the output, and eventually all good things must end. Okay. The language that you are going to learn for dealing with computers is called an algorithm. Okay, an algorithm is just a fancy word for a sequence of ordered steps. Each step is spelled out in minute detail. For example, if you can imagine a fairly stupid kitchen robot, and you have to tell the robot how to make a PB&J sandwich. If you say, get out the bread, get out the peanut butter, get out the jelly, put the peanut butter on the bread. You can imagine the robot taking the jar of peanut butter and smashing it down on top of the bread, right? So you have to go into more detail. You have to say, get 2 pieces of bread out of the bag, put them on a plate, unscrew the peanut butter jar, get a knife, scoop some peanut butter onto the knife. While there is bread that hasn't been covered yet, spread peanut butter on the bread. Okay, that's the kind of detail you need to think in when you're trying to tell a computer how to solve a particular problem. So let's take a really simple algorithm and explore how it's done in a number of different computer languages. In plain English, if you were telling someone how to average 5 numbers, you would say, well, you add up the 5 numbers and you divide by 5. For most computer languages, you can't give them instructions that are quite that simple. There are a few languages we'll see that can actually think in terms of 5 numbers at once, but most computer languages can only handle 1 number at a time. So in this case, I've written this algorithm out in what we call pseudocode. That is, it looks vaguely, it's language that looks vaguely like computer programming code, but it doesn't match any given computer language because it's a little too vague. It's a little more natural language than most real code. So I'd say I input a number and store it as A. I set a loop counter to 4 because I know I have 4 more numbers to add. I input a number and store it as B. So now I've got, say, 1 in A and 2 in B. Add A plus B, I get 1 plus 2 is 3. And I'm now going to store that. I'm going to write over what was in A and store the new value 3. Okay, A is going to hold the sum of my numbers. I decrement my loop counter from 4 to 3. If the loop counter is still greater than 0, I loop back to step 3, input another number, store it as B, keep going. This will happen 4 times, and then A will now be the sum of 5 numbers. So we divide A by 5 and store that as V. I'm going to let V stand for average. Okay, then we just output V. So as you look at how I implement this simple algorithm in a few different programming languages here, I want you to look for a few ingredients of a programming language. First, look for the reserved words. These will generally be typed in a special color. The color doesn't mean anything to the computer, but it's a nice way of showing humans where the keywords are. Reserved words are special keywords that have certain meanings in the language. So if, while, for, read and write in some languages, scan and print in others. So look for what the reserved words are, how many of them there are, and what they're used for. Look at how the programming language uses variables. Variables are user-defined keywords that store values. So some of the older languages only used single-letter variables, A, B, S, V, N. Newer languages allow meaningful variable names like num for number, sum, AVG for average, count for counting through the loop. Look for operators and comparisons. How does it do math? How does it compare values? Look for control structures. There's got to be some way in every programming language to say, if this condition is true, then we'll do that operation. Most programming languages have a way to say, well, for every number between 1 and 5, do this. And most programming languages also have a way to say, while this condition is true, do that other thing. We're not actually going to play with while loops in this example, so you're not going to see those. But look for the if, look for the for. Input, output. Look for how each language that I go through reads values and writes them to communicate with the user. Does it read them from a specific place in memory? Does it read them from a disk or a tape or something like that? Does it write them to the console? Does it write them to a printer or another tape drive or something? And what kind of keywords and processes does it use for handling its input and output? How user-friendly does that seem to be? Okay, so we're going to start with the least user-friendly programming language on Earth, known as assembly language. There's not one assembly language. There is one assembly language for each kind of processor that's made. So the Intel Core series of processors, well, actually all the x86 series of processors have x86 assembly language. All of the ARM processors out there, like the ones that run Apple's iPhones, have an ARM assembly language. This is a made-up assembly language here that is based on features that are found in a lot of different assembly languages. So the load keyword pulls a number out of memory and stuffs it in a processor register. Okay, we're going to pretend that this processor is a really simple one that has registers A, B, and C. So we're going to store 5 in C, and the first number we're trying to average we're going to store in A, and then we're going to load the next number in B. Then we're going to add A and B and store the result in A. We're going to decrement C. So this is very much like that pseudocode algorithm I just wrote, only it's not as easy to read. We're going to do an if jump, that if the value in C is greater than 0, we're going to jump back to the marker that I call loop. So we're going to load the next number, add, decrement, jump again. Eventually, we're going to load 5 into C again, and we're going to divide A, which holds the sum of the 5 numbers, by C, and store the result in B. Okay, and then we're going to store B in the memory location called answer, which is where the user presumably is going to look for the answer. Not easy to read at all. Not easy to write at all. There's a reason that most people do not use assembly language to write their computer programs. They usually use compiled languages that compile to assembly language or machine language. Okay, so some of the first of those compiled languages were written back in the 1950s. FORTRAN emerged in 1957 as a science and engineering formula translation language. Lisp emerged in 1958 as a list processing language, which became popular for AI research. We'll talk about why in a second. ALGOL was an algorithmic language that set many of the rules for the whole C family of languages and many other modern languages like Pascal and Python. And then there was COBOL, which was a business-oriented language, which, believe it or not, is still in use today, mainly because there are some businesses that own some very old mainframes that store some very old data that they still use. And the programs that were written to run those databases were written in COBOL. So every now and then there will be an ad in the programming classifieds that says, needed one COBOL programmer. So if you happen to learn that language, you might be in high demand. In the late 1950s, you can see in the upper right corner there what a computer looked like. It would not have been a single box like you see a computer today, but a series of boxes that filled, the better part of a room. And most institutions were lucky to have one computer. There was one IBM 650 at Texas A&M in the late 1950s. Okay, so here's FORTRAN. You can see that the input-output are read and write statements. And here it's assuming that there is an input tape drive that's giving it input details, and output tape drive that's giving it output details. The computer at this point did not have a keyboard. You entered your program in something called punch card format, and you would have a stack of these punch cards that you would have to have in exactly the right order. Woe be to he who dropped his stack of punch cards. And you fed the cards into a card reader in the computer, which would then analyze your program. You could give it more, input values as punch cards, or you could put the input on digital tape, such as is reading here. This is writing to an output tape. It could have instead written to a printer and just printed out a line of output, but there were no computer screens at this time to look at your output on either. So we read from the input tape our number A. We set our counter to 4. We read from the input tape number B. FORTRAN is called FORTRAN because it was the first language to allow you to just write mathematical formulas exactly as is. So you can say A equals A plus B, N equals N minus 1. Real simple stuff. The if statement in FORTRAN was kind of complicated. If you had a negative number, it would do the jump to the first code point there, the first line number. If you had a 0, it would jump to the middle line number, and if you had a positive value, it would jump to the third line value. So as long as n is greater than 0, we're going to jump back to 701, read another B, and keep going with our program. Eventually, we'll have run through all 5 numbers, so we jump to 801, and we say V for average equals A over 5.0. Then we write to our output tape the phrase average equals, and then a floating point number with 10 digits and 2 places after the decimal point is what that F10.2 means. Lisp is a programming language of a completely different kind. If you can read this, you are a star programmer. Essentially, each set of parentheses in Lisp is a function that the first item in the list tells you what it's going to do, and then every other part of the list is an operand to that function. So plus 12, 23, 34, 45, 56 means add up those 5 numbers. Divided by the result of that sum, 5, means you take the result of that sum and you divide it by 5. Right, and the result of everything else means you wait until you've done all that calculation and then you write the value to the screen. Lisp has got a funny history because it was invented by a fellow at MIT, a computer scientist, as a purely theoretical language. He didn't think there was any use in ever actually writing programs with it. He just thought it was a neat thing to show that he could write a programming language this way. Then a couple of years later, a fellow named Steve Russell implemented this in IBM 704 machine language, and we were off to the races. Lisp has spawned many variants over its history, including a fairly famous one called Scheme and another fairly famous one called Common Lisp. As you can see, it was still in use in 1984. Well, it's still in use today by artificial intelligence researchers, because this language, unlike most other languages, the structure of the language itself is just a series of lists. So this kind of program can actually dynamically rewrite itself because there's no difference between data and code. It also is very good at doing English language processing, which is natural language processing is a big deal in artificial intelligence these days. Moving up a decade to the 1960s, computers looked a little bit more like this U Manchester Atlas in the upper corner. We might have one series of boxes there with some peripherals, a printer and maybe a screen and some other things. And you now would interact with your computer through something called a terminal. You might have a little box sitting on your desk like this one shown in the screen there. It had a keyboard and it had a very small black and white screen that just showed text. It didn't show any graphics. It didn't show anything fancy. You typed on the keyboard and letters were sent through a little telephone line to the computer. The computer interpreted them and it sent letters back to your terminal telling it what to print on the screen. It was slow, it was painful. If you mistyped something, you were SOL. Okay. 1962 saw Simula, the first object-oriented language for simulations. We'll see what object-oriented means at the very end of this course in C++. CPL and BCPL were sort of the forerunners of C. We're not going to talk about them much. And 1964, a fellow at Dartmouth College up in New Hampshire, actually a pair of fellows. Now, before I show you this algorithm in BASIC, I'm going to update the algorithm slightly because we're now getting into languages that allow more meaningful variable names. So we're going to have one called sum that's going to start at 0, and then we're going to do a for loop counter, okay, from 1 to 5 because we have 5 numbers to add. And then for each pass through the for loop, we're going to input a number, store it as num, add num to sum, and store it as sum. Then when we've ended the for loop, sum is going to hold the sum of 5 numbers, so we're going to divide by 5 and store that as average. Okay, and then we're going to output the average is average. Well, this is pretty much what that looks like in BASIC. Now, BASIC used line numbers, sort of similar to how you saw us use with FORTRAN, and there was a lot of jumping from line number to line number in your average BASIC program, but they did have a structured for loop. So you could say for C equals 1 to 5, do two things: input a number, add it to sum, and then you say next C, and that jumps you back to the for loop. And you keep doing that from 1 to 5, and then average is sum divided by 5. Note that the input statement is really fairly user-friendly. You say input, and you have a prompt for the user to read, and then you tell it what variable you want to input. The print statement is also fairly user-friendly. You say print, you can put text in quotes, and then after a semicolon, you can tell it what number you want to print after your phrase in quotes. BASIC went viral, as they say today, and it became practically a requirement for 70s and 80s era computers to include a BASIC interpreter or compiler in their, when you bought your computer. Microsoft actually didn't phase out MS BASIC in their DOS Windows systems until Windows 2000. It was considered that popular or that necessary. For a whole generation, that would be my generation, kids grew up with textbooks that had little try it in BASIC enrichment pullouts, where you would actually be encouraged to do a little, play around with a little computer programming by writing your own BASIC code to solve a math problem or a physics problem or something like that. The 1970s, we took a step forward in complexity and readability of languages at the same time. Pascal was another attempt at a teaching language, kind of similar to BASIC, but much more structured. C was much less readable than Pascal, but flexible, powerful, and has become kind of the winner and champion among system programming languages. SQL came out in 1973, and that is also kind of a winner and still champion of database languages. Pascal looked like this. You can see that the language was very structured. You had to declare the name of the program. You had to declare your variables up at the very top. Then you had a begin statement, and then you could start writing your code. They had a colon equals, which is sometimes read as gets value or becomes. So sum gets the value 0, count gets the values from 1 to 5. Then you had write statements and read statements. Unlike BASIC, you had to write something out to the user to prompt them before you did a read. And then you would read one number every time through the for loop, and sum becomes sum plus num. Okay. Average then becomes sum divided by 5, and we have a write line statement to write a line of output to the user. C, to a practiced programmer, looks almost the same as Pascal, but to a newbie, looks a heck of a lot less readable. Instead of begin and end statements, we have curly braces, they call them. Instead of having a program such and such, we have int main. Instead of declaring our variables up at the top in a var section, we just declare variables as we're about to use them. So double num sum, int count. The for loop is a heck of a lot less easy to read. It's much more powerful than the for loop in any other language that's ever been written, but it's a lot less easy to read. We'll get into that in a much later part of this class, so I'm not going to break down the for loop for you right now. C had printf and scanf. The F standard for formatted, so there were ways to put in formatting codes like the %f in the scanf that told it to look for in scan mode or to print in print mode. a floating point number. So floating point numbers are numbers that have something after the decimal point, 3.4 or 5.2 or something like that. There was a shortcut operator called plus equals that sum plus equals num is the same as saying sum equals sum plus num. It's a shorthand. It makes it a little harder to read, but it makes the code more compact, and it actually matches the machine language that you're compiling to a little bit better. Finally, we say double average equals sum over 5, and then we printf the average is %f, insert a floating point number there, and where do you look for the floating point number? At the end of the printf statement, it's going to be the word average. In the 1980s, C was expanded with classes or objects, and that was renamed C++ in 1983 as a pun on the ++ increment operator in C. 1983 also got Ada, named after that Countess Ada Lovelace, who was the first programmer. It's an object-oriented and safety-first language extended from Pascal, which became the required language for use in Department of Defense projects because it was so safety-minded that the programs just almost never crashed. Required so much debugging ahead of time, but once you had a program ready to deliver to DoD, they were pretty sure that their missile defense system or their airplane navigation system or whatever was not going to crash in the middle of a critical mission. 1984 gave us MATLAB, which stood for Matrix Laboratory. Many people think it means Math Laboratory, but the MAT stands for Matrix. It's a language specifically designed to do matrix math, which tends to come up a lot in math, science, and engineering. This is the only one of these languages that has never been open sourced. Okay, if you want to write a MATLAB program, you have to buy a very expensive program from the MathWorks to write and run MATLAB programs. And in 1986, there was Objective-C, which is a competing standard for C++, a different way to add object-orientedness to C that's not at all compatible with C++, and was not nearly as successful as C++ until Apple chose it as the way to write programs for their new Mac OS X in the early 2000s. You can see at the top of the page what home and office computers looked like in the 1980s. Home computers were still pretty rare in the 1980s, but your office might have one of these computers sitting on it. If you were really wanting to do serious computation, though, you still probably were working on a terminal program that connected you to a mainframe, a big computer somewhere down the hall in a computer room. C++, you'll notice, looks almost identical to C. That was the whole point of C++, was to take something people already were familiar with and just add some extensions to it. The main difference you'll see is the input and output. They use these output stream objects called cout and an input stream object called cin, and you can just insert output into the output stream and extract input from the input stream. You don't have to format your output in any particular way. You just, though there are output operators that we'll learn in this class. So to put out the average is average, you just string a number of those output operators together and stuff all that output into the cout object. MATLAB is one of those rare languages that actually can think in terms of multiple numbers at once. So to solve our averaging 5 numbers in MATLAB, we just say A equals, and we build what MATLAB calls a vector, a one-dimensional matrix, out of the 5 numbers we want to average. Then we say average equals sum of A divided by 5. And MATLAB, which is built to work kind of as a calculator, will just display average equals 34.5 for you there on your workspace. Now, MATLAB is interpreted, so if I had to write this as a for loop, stepping through each number and adding them up a little at a time, that would actually be much slower than the version in C++. But when I use its built-in matrix functions, MATLAB is comparatively fast. And also, as I said before, MATLAB is proprietary. You can't just download a MATLAB interpreter off the internet. You have to buy the MATLAB code from the MathWorks. The 1990s saw an explosion of new programming languages. Python, Visual Basic were both attempts to create readable programming languages. R was an open sourcing of an old statistics and data processing language called S. This is something you'll find very common in computing, is that we like naming our things with jokes. So C++ is a one-level increment from C. Python is actually named after the Monty Python comedy troupe in England. And R is one letter different from S. So there you go. Java was named after a common euphemism for coffee, and its logo actually is a little coffee cup. Java was an attempt to create the ultimate application and web applet programming language that would let you write once and run everywhere. The people who developed Java expected that before long, everyone would have a Java virtual machine installed on their computer, and so people could just write one program and it would run on every computer in the world. For a little while, they were right. That worked pretty well. You could go to any web page that had a Java applet, and it would trigger the Java virtual machine on your computer to run that applet. But there have been some security problems with this, and so in recent years, Microsoft and Apple have taken the Java virtual machines out of their operating systems, and you now have to go and specifically fetch one, download it, install it on your computer if you want to run Java. So it's a lot more complicated than it used to be. Or you can go with the solution that programs like the Minecraft Java edition do, which is you install a mini Java virtual machine with your program that just lets it run on the computer you've downloaded it on. And in 1995, JavaScript, which has been made fun of because it actually has no relation to Java except that they both use a C-like syntax, JavaScript was a scripting language that could be run in a web browser. And this became a cornerstone of website design. Any website that has any kind of interactive element where you click one thing and the website changes, or you hover over something and something happens, it requires JavaScript to do that kind of on-the-fly changes to the web page. Okay, so here's what our sum for 5 numbers looks like in Python. We start with sum equals 0. For count in range 0 to 5. Python's for loop does not have an actual counting mode like other languages, so you have to give it a range of numbers to count through. And the Python range function generates one number less than what it looks like it should. So instead of giving you 0, 1, 2, 3, 4, 5, it actually doesn't give you the 5. So it gives you 0, 1, 2, 3, 4, which ends up being the right number for us to enter our numbers to average. So you take an input, enter a number to average. Like BASIC, it gives the input statement, lets you prompt the user for input. Unlike BASIC, every input from the user defaults to being a string of text, so you have to specifically convert it to a floating point number and store that as A. Modern Python has the same plus equals operator that C++ does, so sum plus equals A, and then average equals sum over 5, and then you print the average is, comma, average. Real simple, generally pretty readable, and once you get the hang of the language, not too hard to do. The 2000s, we didn't see quite as much excitement in the programming language world. C# came to be. It was a language that is like Java in the way that American English is like British English. You know, they have mostly the same basic ideas, but a lot of important differences in the details. Scratch was a visual programming language developed at MIT's Media Lab aimed at teaching coding to kids. You may have seen various implementations of Scratch where you drag little blocks of code onto a visual programming space. F# was a function-first programming language. PowerShell is an object-based scripting environment for Microsoft. It's a very different way to write scripts than anything people were used to before. And Google wrote Go in an attempt to improve on C that is, at this point, mostly used by people at Google. This is what our program would look like in F#, just to show you something completely different. It's similar in a way to MATLAB and Lisp in that it can deal with 5 numbers at once, so you can just create a list of 5 numbers, pass it to the list.sum function, and then pass it to a function you created called div5, which just takes a number and divides it by 5. Then there's a print function that says the average is %f, and you give it your average. Finally, in the 2010s, we saw a bunch of incremental improvements on programming languages. Rust is an improvement on C++ with better memory safety. TypeScript is Microsoft's attempt to give JavaScript type safety. Swift is Apple's attempt to improve on what Java and C# started and create the sort of ultimate app development programming language, which finally replaces the ages-old Objective-C. Again, one of the big emphases was on safety. See a pattern? There's not much in the revolutionary development right now. More, we're just trying to improve code safety in all these other languages. The most popular languages continue to be Python and a whole lot of derivatives from C. You can see here on this graph of programming language popularity over time that Java has declined a little bit over the last 20 years. Python has risen a little bit over the last 20 years, mostly in the last 5 years, actually, as it's become one of the main languages for big data. C has stayed pretty close to the top. That's the little black line there. C++ is the orange line. It's gone down a bit, then it's come up a bit, then it's down a bit, then it's come up a bit. It's on the way up at the moment. But the thing is, if you take C and Java and C++ and C# and you add those 4 lines together, they make up more than 50% of all the programming that people do these days. And they all use the same syntax. They all use the curly braces and the same for loop and the same while loop and the same if and else, and all those keywords are the same. So where do you want to start in learning to program? I say you want to start with one of the C family languages, because once you know that, you can pick up any of the other ones fairly quickly. So we're going to start in this class with C++, because we can start with simple programming with, simple procedural programming with no object-orientedness or any even needing to know what a function is until we get to that, and we will get to that in this class. So hopefully this encourages you to follow up with the rest of the class and start learning to program. Till next time, good luck, happy programming, and I'll see you in the next lesson.